So an outcome is just a possible result. An event. Event is just an outcome that we're interested in. So our event for our coin was flipping a heads. Our event could be rolling a 7 on 2 die. Our event could be multiple outcomes. Our event could be rolling a 7 and then rolling a 3. That could be our event. So that's 2 outcomes, but the event is the 2 together that we're interested in. So event just means the thing that we're interested in. And one other word that comes up frequently when we're working with probability is sample space. The sample space is all possible outcomes. So for our coin, what's our sample space for our coin? And we have there are 2 events in the sample space. And what are those 2 events? Heads and tails. That's a sample space for a coin. The sample space for our 2 die would be that chart that we filled out on the back of our sheet yesterday with all 36 of the possible ways that we could get different combinations of numbers coming up on the die. So the sample space just means what are all the possible outcomes. When you describe the sample space, you don't necessarily have to, if we wanted to describe the sample space of the 2 die, we'd have to write down all 36 numbers. But we could say instead, we say the sample space is all the possible combinations of the 2 die. We don't usually write down the entire sample space. For a coin, it's pretty easy, heads or tails. Sometimes the sample spaces can be extremely big, and it's hard to describe, hard to write them all down. But a sample space just means all of our possible outcomes. Any questions on our vocabulary here? Okay. Couple of important things about probability. Just to help you to make sure when you do a calculation, if you do something comes up, you know that it makes sense. Always a number or a fraction between 0 and 1. Or if we're writing it as a percent, 0% and 100%. So if we have a probability of 0 or 0%, what is that telling us? Never going to happen. It's impossible. Someone in the last class gave the example of if we have a container that has red and green marbles, only red and green marbles, what's the probability of reaching in and pulling out a blue marble? 0, or it's impossible. It can't happen. And what about a probability of 1? What does that tell us? That's always true. It has to happen. It's certain. The probability of the pen falling when I let go of it is 100%, because gravity always works. On Earth, right. All right, are we good with this? And this is all, I think, all things that we have a pretty good idea of after we talked yesterday. I think most of us have a pretty good idea of these ideas about probability. So let's talk about experimental probability, and then we'll do an example. So our experimental probability is the same, it's the same idea, but instead of using what we know about a particular thing, about a particular situation, we do an experiment. We flip coins and we count. We roll die and we count. But we do the same kind of calculation. The probability of an event is number of favorable outcomes divided by the number of times we do the experiment. So when we flipped our coin, we flipped it 10 times. So the number of times we did the experiment was 10. We divided by 10 when we did our opener. Our favorable outcomes, we counted how many times we got heads. It's still the same idea, favorable over total. But for these, we're counting, we're doing an experiment, we're measuring, and we're counting for experimental probability. But it's the same idea. Questions on our vocabulary on how we calculate probability? All right, let's do a couple of examples, and then we have one other thing to talk about to bring our lesson together today. All right, so we work in a Texas Instruments calculator factory, and we were in charge of a production run. We made 15,000 calculators in our production run. And we want to estimate how many defects there might be in that entire production run. So we want to do some quality control. So we want to estimate how many defects. So we don't want to test all 15,000 calculators. That would take too long. That would cost us too much. So what we're going to do is we're going to pull out 450. We're going to test 450 of them. And in that test we found 4 defects. And what we're assuming is that the same percentage of defects would be in the entire production run. So we want to use our test to decide how many defects would be in the entire production run. So is this going to be experimental or theoretical probability? Theoretical?
Well, the test is going to be experimental, but you can have to figure everything out.
Right. So the test is we're doing an experiment. So for this we're calculating experimental probability. So how do we, from this test, how are we going to calculate our probability of a defect? What's our favorable event for a defect? 4, because we have 4 defects. So our probability, I'm going to say probability of a defect is 4. And how many times do we do the experiment? 450 times. So our experimental probability of the defect is 4 out of 150. If I plug that into my calculator, I get 0.0089. If we wanted to write that as a percentage, remember to turn a number into a percent, move the decimal place over by 2, and multiply by 100. This would be actually 0.89%.
How does it affect this?
0.89%.
Out of 50,000.
That's our estimate. So 0.89% are going to be defective based on our experiment. So how do we figure out how many of the 15,000 that's going to be? Find 0.89% of 15,000. And from what we have here, how do we do that?
15,000
Do we-
0.0.
Do we divide?
Oh, no.
Multiply. There we go. Is that what you were going to say? So we're going to multiply 15,000 times 0.0089, and that gives me 133.5. Can we have 0.5 of a calculator? No? So, no, I had done it before. So we're going to say that this is, we're going to round this up to 134 calculators. So we're going to estimate that out of 15,000 calculators, 134 are defective. I don't know if that's good or bad for a number of defects in calculators, but that would be what we would estimate. Now the hard part would be to figure out which ones are defective. Questions on our calculation? Everybody good? Looks accurate? Okay. All right, let's do another example going back to what we did yesterday. We're going to roll 2 die. And our worksheets, the books on probability, I don't know why, they call them number cubes. So I think the reason they call them number cubes is because when we think of dice, we think of 1 through 6 being on the sides of the dice, and a number cube doesn't necessarily have numbers 1 through 6. You could make number cubes with different numbers, but when you talk about a standard number cube, they're talking about dice. So we have 2 die, and we want to know the probability of rolling 9. So the 2 numbers adding up to 9. So we want to calculate probability of 9. So we did some work yesterday that's going to help us out here. For our number of possible outcomes, how many outcomes did we have for 2 die? The grid on the back of our sheet? 36. We had 6 this way and 6 this way. When we filled out our grid, we had 36 numbers in it. 6 times 6 is 36. So the number of possible outcomes is 6 on one die, 6 on the other die, 36. We had 36 numbers in our grid yesterday. And I'm going to put, we don't have to do this for every problem. I just want to write it up for this problem so we know what our, just to use some of our vocabulary. Our sample space. So our sample space is all 36 possible outcomes. That would be our sample space for this problem. Our event, the thing that we're interested in, is a 9. So that's our event. How many favorable outcomes do we have for rolling a 9? How many ways can we roll a 9? Do we remember? This is what I usually have to do. Die 1 and die 2. So let's start with the first die. If I roll a 3 on one die, what would give me a 9? A 6. Just going to go up by 1. A 4 and a 5. A 5 on this die. 4 on that die. And a 6 on that die. And a 3 on that die. All of those equal 9. So our favorable outcomes we have 4 favorable outcomes for a 9. So our probability is favorable over possible, or total, equals 4 over 36. That's favorable over total. And I'm going to reduce that, and I get 1 out of 9, which is about 0.11, which is about 11%. So that's our probability of rolling a 9. About 11%. We have about 11% chance. Questions on that example? Everybody good? The favorable, so I just looked at all the different ways I could roll a 9 on 2 die. So if I got 3 on one and 6 on another, that gives me 1. A 4 on the first one and 5 on the other gives 9. So and I have 4 combinations that give me 9. Okay? No worries. And if you're not sure how to figure out with dice, that kind of thing, to figure out the number, just write it down and write down your combinations that add up to the particular number. Okay? All right, one last thing to talk about and then we're done. Complements. And notice it's spelled with an E, not an I. So we're not talking about saying nice things about each other. So a complement, what we mean by complement in probability is the complement is everything that's not our event. So it's kind of the opposite. So with our coin, our event for our opener, our event was flipping a heads. The complement would be flipping a tails. For our die, the last example we did with rolling a 9, the complement would be rolling everything other than a 9. So it's everything possible that can happen other than the event that we're interested in. So that's our complement. So what we're going to do with the complements are kind of nice to work with. The probability of the event plus the probability of the complement. And I'm going to put in parentheses down here, not the event. What is that going to have to equal? Sample space, or all the possibilities. So the probability would be 100%. The probability is all the possibilities. The event and everything that's not the event is everything that's possible that can happen. So the probability of the event plus the probability of the complement has to equal 1. So with our coin, the probability of the heads and the probability of the tails, those are all the possibilities. The probability of a heads or tails coming up when we flip a coin is 100%. Probability is 1. So the probability with our die, the probability of rolling a 9 and the probability of rolling every other possibility that's not a 9, those together are all the possibilities that we have. So the probability has to add up to 1. So our probability of our complement, the way we usually use it, and I'm just going to write comp for complement, equals 1 minus, if I subtract the probability of the event from both sides, 1 minus the probability of the event. So in our previous example, we found that the probability of a 9 was 1 out of 9. So the probability of not a 9, which is our complement, is 1 minus 1/9. To subtract or add or subtract fractions, I need a common denominator, so that's 9/9 minus 1/9, and I get 8/9. The probability of rolling a 9 is 1/9. Probability of rolling anything other than a 9 is 8/9. If I add 1/9 and 8/9, I get 9/9 or 1. So probability is 1.
So the probability of
Probability of the 9 and everything that's not a 9 altogether is 1.
so what's the probability of
That's the probability of the complement. So if someone asked you what's the probability of rolling anything but a 9, the probability would be 8/9.
So isn't that basically the complement?
That's the complement. Yes, that's exactly what we're saying. Is that's the complement. Okay, that's all I was saying. 8/9 is the complement of 1/9. And if I add 1/9 and 8/9, I get 1. Okay? So that's how we work with complements. So if we had, let me give you another quick example. We had marbles in a bag, and we have, say, 3 red, 3 blue, and 2 green. And we want to calculate the probability of pulling out anything but a green. So any other color but a green. We calculate the probability of pulling out a green and subtract that from 1. So that's all there is to complements. All right. Questions before we stop? We just have a couple minutes left. All right. Let me give you your homework.